In this talk, I'm going to introduce mean field models on carbon emission and taxing. This is a joint work with René Carmona and Mathieu Leroux. First, I want to introduce the electricity markets. We have the producers and they sell the electricity they produce to the grid. And the price of the electricity is determined by the supply and the demand by end users. We are going to have the electricity producers as our players, and they are going to use renewable and non-renewable energy to produce the electricity. We are going to also have a regulator, and this regulator is going to use a carbon tax to control carbon emission levels. Here you can see some countries that are using or are planning to use a carbon tax as a mean to control carbon emission. So why are we using mean field games? If there are a large number of players in a game, it is very hard to find the Nash equilibrium. If we assume the number of players are going to infinity, then we can use the mean field games methodology. But we should have further assumptions. For example, players should be symmetric and infinitesimal, and there should be mean field type interactions. And here are some references. Mean field games is introduced by Leslie Lyons and CAIMS and Malame around 2006. Probabilistic approach is introduced by Carmona and Leroux. Mean field games with Stackelberg equilibrium papers are written by Bensosen et al., Eli et al., and Carmona et al. And there are some other papers on the energy-related applications with mean field models. But in these papers, they didn't investigate the carbon tax and carbon emission levels together. So we are going to have two steps in our talk. First, we are going to introduce the mean field model with only minor players. Then we are going to add the regulator. So let's introduce the minor players model. Minor players have two controls. The first one is the change in the non-renewable energy usage. This is time dependent and it is going to be denoted by NT. The second one is the number of solar panels built. This is going to be denoted by RE and it is time independent. Here, for the sake of simplicity, we use the solar energy terms, but we can use other types of renewable energy too. For if you start to the states, we have the first state, sun irradiance. This is an Ornstein-Uhlenbeck process. And the second state is the electricity production. The third state is the emission level. Fourth state is the pollution, and the fifth state is the non-renewable energy usage. Here we can see that the average electricity production is coming from the production from non-renewable and production from renewable. For the production of renewable, we have a sinusoidal trend and also noise part, but for the non-renewable, we don't have a noise. If we start the objective, the first term is the penalty to ramp up or down the non-renewable energy electricity production facility too fast. And the second and the sixth term, these are the costs from non-renewable and renewable energy, respectively. The first one, here the difference is that non-renewable energy has a variable cost, renewable energy has a fixed cost. The term 5 is the cost of carbon tax. Term 3 is the desire to match the demand, and DT here is the demand, which is exogenous. The fourth term is the revenue from electricity production. Here, this part here with rho 0 and rho 1 is the inverse demand function. So let's start the equilibrium notions. The first one is the social optimum. Here we are assuming there's a social planner or the players are behaving cooperatively. In this case, our problem is becoming an optimal control problem. The second equilibrium is a Nash equilibrium, and we can use the mean field game setting for this one. And here we assume that players are giving their best response to the other players' decisions, and they are non-cooperative. And the equilibrium here is found by fixed point arguments. If we check the mathematical definitions, we can see the difference here. In the social optimum, when the representative player changes their control, it affects the mean field too. But in the Nash equilibrium, in the mean field game setting, when the representative player deviates, the mean field stays the same. So let's start the solution approach. Here we are going to assume that RE is fixed. When RE is fixed, our problem becomes a linear quadratic and the only control is the NT. If we introduce the mean state vector xt, we can also show the numerical algorithms. So the algorithm for mean field control is going to be called as social opt. Here we are going to have a grid search for RE. So we are going to fix an RE and we are going to solve the Riccati equation and the ODs to find the x bar t. Then we are going to calculate the corresponding cost with respect to RE. And then we are going to find the optimal RE that minimizes this cost and we are going to return it. The second numerical algorithm is the algorithm for mean field gain. Here we are calling the function Nash egg, and the differences are denoted with blue. Here we need to have the fixed point argument, that's why we have this while loop here. We are introducing the mean field, and as long as this mean field is not converging, we are doing the grid search for RE inside. Then when the convergence happens, we are returning the optimal values. Let's start some experiments with only minor players. Here in the first experiment, we have the minor players cost. Here we are calculating the minor players cost with respect to C2, which is the coefficient for demand matching, and with respect to tax. And we can see that as the C2 and tax is increasing, the cost of minor player is also increasing, both in MFC and MFG setting. And here also we can check the price of anarchy. Price of anarchy is showing us how efficient the Nash equilibrium is. If it is closer to 1, then it means that the Nash equilibrium is close to social optimum, so it's efficient. So here we can see that if the tax levels are high or the C2 is high, the price of anarchy is getting lower. This means that the Nash equilibrium is more efficient and we may not need a social planner for making everything more efficient. The second experiment is on the production levels. Here in these plots, we are showing MFG and MFC models at the same time. And we have different 2 and C2 values fixed. This is an overtime plot. Here with the green part, we are showing the demand, and this is at the same level. The blue part is the production from renewable. The purple one is the production from non-renewable. The orange one is the production in general. Here the solid lines are the MFG and the dotted lines are the MFC. Here we can see that if the tax is 0, there is no incentive for producers to invest in renewable energy. So in both MFG and MFC, we have renewable levels at 0. Also, we can see that since the demand matching is not important, there is no demand match here. In the second one, we are increasing the tax, and we can see here that the renewable energy is used. So there's an initial investment for renewable energy. We can see that in MFG, actually, renewable energy is higher, but this is not necessarily good because non-renewable energy levels are the same. And this excess investment for renewable is actually used for overproducing. So in the MFG case, we can see that production is more than MFC. And when we also increase the C2 value, so demand match, if the demand matching is important, we can see that we are matching the demand as much as possible. And we can see that MFG and MFC, they are behaving the same. So let's start the regulator's problem. Regulator is going to have 2 controls. The first one is the carbon tax level. This is going to be denoted by tau. The second one is the penalty to electricity producers for not satisfying the demand, and this is going to be denoted by C2. This was the coefficient of the demand matching in the minor players. So the objective of the regulator's problem has 4 terms. The first part is the penalization for having high pollution. This is the goal pollution level that the regulator wants to have. And if we are higher than that, we are having a penalization. The second term is the revenue from taxes. The term 3 is the desire for having lower taxes. This can be coming from the fact that they want to get re-elected, for example. And the term 4 is the demand matching. Here we took the importance to the demand match from minor player level to the regulator level. Here we can't see the C2 in this objective function, but this is not weird because this C2 is affecting minor players model, and minor players solution is gonna be coming here through P big T bar and QT bar. So it's gonna affect this function indirectly through minor players model. So we have two equilibrium notions in this part. The first one is the Stackelberg equilibrium with MFC. In this one, regulator is assuming that there is a social planner or the minor players are behaving cooperatively and the population is at the social optimum. And according to this assumption, regulator is choosing 2 and C2 levels to minimize its cost. And the second equilibrium notion is the Stackelberg equilibrium with MFG. The regulator assumes that minor players are not cooperative and that the population is at Nash equilibrium. And the regulator is choosing the 2 and C2 couple to minimize its cost. This here, Stackelberg equilibrium with MFC, is a new notion that we are introducing. So let's start the numerical algorithms. First, I'm going to show the numerical algorithm for Stackelberg equilibrium with MFC. Here we are going to do grid search for 2 and C2. So we are going to fix a 2 and C2. We are going to compute the X bar using the algorithm social opt that we introduced before. Then we are going to calculate the regulator's cost. And we are going to return the optimal 2 and C2 couple that gives the minimum regulator cost. If we are using the MFG, Stackelberg equilibrium with MFG, the only change is going to be here. We are going to use the algorithm Nash-Egg. So let's start the experiments with the regulator. Here we are introducing the notion of not accepting the contract for the minor players. So if the cost of minor players are too high, they may decide that, that they don't want to produce. So we are checking, given a C2 and tax, which are the controls of a regulator, whether these minor players are accepting the contract or not. We see that in both MFC and MFG setting, minor players are not accepting the contract if C2 and tax levels are too high. Also, we can here see the surface of the measure of the regulator's cost. Here we can see that in the MFC and MFG setting, the regulator's cost is similar, but actually the minimizers at different points. So in conclusion, we showed the mean field control and game models on carbon taxing, and we added the regulator to the model. We discussed different types of equilibrium notions, and we analyzed the numerical solutions corresponding to these equilibrium notions. For the future work, we are planning to further investigate the regulator problem, and we want to have a multi-population setting. And also we are planning to use different numerical solution approaches too. If you want to contact me, you can use my email. Thank you very much for listening.